Now in this video I will use Matlab Simulink utility to simulate the performance of a mass spring system. First start Matlab, then from the home menu start Simulink. Now on the Simulink start page, start a blank model. And in this white space, we will build the mass spring system model. Let me start by adding an image of the model system. Let me add it right here. I have the images already prepared and stored. Here's the system we will be talking about, a mass spring system with an external force F of t. First, the equation of motion of the system is clear. It's mx double dot plus kx equals the force F of t. Now to build the model, I will start by rearranging this equation of motion so that the acceleration of the mass is on one side of the equation and the rest of the inputs on the other side. First, let me define the variables of the motion of the mass, namely the acceleration, velocity, and position. To do that, I will start the library, which contains all the blocks available in Matlab Simulink. I will go to the continuous library, and from the continuous library I will click and drag and drop an integrator block, and then I will add another integrator right here. Now connect the first integrator to the second. Here's the input to the first integrator and the output of the second integrator. Now if the input to the first integrator is the acceleration of the mass, let me call it ddx for x double dot, then if we integrate this, we will get the velocity dx or x dot. And if we integrate x dot one more time, the output here will be x. Just x. So now I will have the three variables in the system: the acceleration, velocity, and position, x double dot, x, and x dot. Now if we go back to the rearranged equation of motion, I will notice that the acceleration is basically the sum of two quantities, basically the force minus the kx. So I will add a sum block. You will find that sum block under commonly used blocks. Right here there's a block called sum. So now let me connect that here. Now that means the acceleration ddx is the sum of two quantities right here. Now one of the quantities is negative, so I will double click the block, open the properties box, and change the second input to negative input. Now I have a plus minus sign. So if the input here it's f of t minus kx, so the f of t will be on the positive input, kx will be on the negative input. So from the negative side I will go back and connect it to the x. Now x is the input here, the negative input, but x is multiplied by k, so I will add a gain that's under commonly used blocks also. Gain. Drop it here and then click, drag it over the line, and it will automatically be inserted in the line. Now it's k multiplied by whatever gain we have here, and input as a negative input to the acceleration part. Now for a force, I have many sources here. Under sources, I can input forces in many forms. A ramp, a step, a sine wave. I will, for simplicity, now use a step input. Click, drag, drop, and right here, and then connect it. Now, if I call this f of t, now this is my input, f of t minus, and this gain, I will call it k, the spring constant. So it's x times k minus negative sign. So it's f of t minus x times k. Now to view x, the output, I will use a scope. It's under sinks. Click, drag scope. It's basically a way to visualize graphically the output. Now here I have my model. There's one final step that I need to add. Let me extend this a little bit. The final step I have to add after summing the two quantities is I have to divide the sum by m. So I will also add another gain block. So it's the sum multiplied by a gain, and this gain will be 1 over m. So it's now 1 over m times f of t minus k times x. And that's exactly the equation that we have here, which will produce x double dot. Integrating x double dot will result in x dot. Integrating one more time, and I will have my x. Now, let's put some values to the m and k. Let's say the spring constant is 8, and let's say that the mass is 2 kilograms, so it's 1 divided by 2, 1 over m. Now let's open the scope and see what's going to happen when I hit the play button right here. And here's my response, a sinusoidal response, which is expected since there's no damping in the system. Now notice that the line is a bit broken because the default step size is automatic selection in Matlab, so it might be a little too big so that the line is broken. So I will have to go to the modeling menu and then click on model settings, and in model settings, the solver options, you see here the maximum step size is set to auto, so I will change that to a smaller value. Let's say 001. Now the step size cannot exceed this value. Hit OK, and then let's open the scope one more time and rerun the simulation. Now you can see that the simulation and the response is smooth. Now the input was a step function. Double click. Step time 1 second. That's when the step happens. It starts from 0 and the final value of the step is 1. Now if I want to see the step input along with the output of the system, I can use right click here to branch a line and then take it to the scope. Now basically what's going to happen is that the scope will display both the input and the output signals. Let's go back to the scope and hit play again. Now here we see the input signal, the blue line. It's step function, value of 0. At 1 second it steps up to 1, and the response is a sinusoidal response right here. Now the selected values for the mass and the spring constant were 8 for the spring constant and the mass 2. So if you solve for the frequency, omega n squared is k over m. So omega n squared is going to be 4 basically. So the natural frequency is 2. And for a natural frequency of 2, the period of the system is 2 pi over the frequency, which makes the period 1 pi. And now if I view here, if I look at the response and try to estimate the frequency or the period of the response, you will notice that the response starts at 1 second and completes a full cycle at 4 point something. So it's 4 point, I can zoom in, it's 4 point, you can keep zooming in, it's nearly 4.14. That's where a complete cycle happens, starting from 1 second. So the period of the complete cycle is actually 4.14 minus 1, that's 3.14, and that's a pi. So here we have our response, frequency 2 radians per second, period 1 pi, input of 1, and here's my output. Now I can also play with the input. I can set the step time to 0 so that the input starts right from the beginning of the simulation. Now the step, if you play, will start at time 0, a full cycle, and then 3.14, that's the period, and here's my response. Now you can use different inputs for the system. This was step input. You can use, if you go to simulation and you open the library browser, you have in sources many options for the input. We will later on try to use the different options here based on our problem. Now one other tool or option that I can use to simplify the view of the model. The model, later on when you have larger models, you will have cluttered space here, workspace. So you can clean it up a little bit by here selecting the model part. Here's my part. Now a menu options here appears, and you can, from the first option, create a subsystem. Click here. Now all the model and its content are placed into a block. You can see here a shadow image of what's inside this block. If you double click the block, it will take you to the inside, and what we have on the inside is the model of the system that I started with. One input and one output. You can name these. Click here, it's N1. I can name this as force, and the output, click, and double click on the name. The default name is out1. Change it to X. Now going back with this back arrow, I will go to the original subsystem, and the input is force and the output is X. Now the workspace is a little bit cleaner. You can name. Now the blue names that appear on the blocks here, when you click away from the block, they will disappear because these are the default block names. When you change them, for example, double click on the word subsystem and change it to mass spring model. Now the color will change to black and the model name will continue to appear. This way now I have a clean model of a mass spring system simulation.